The physical transformation of a pure substance refers to a change in the physical state of a pure substance without altering its chemical composition. This is also known as a phase change. Examples include the solid to liquid transition, called melting, the liquid to gas transition, called vaporization, the solid to gas transition, called sublimation, and various types of solid to solid phase transitions. This chapter covers the thermodynamics underlying the spontaneous phase changes of a pure substance at specific pressures and temperatures. Let's begin by defining a phase. A phase is a form of matter that is uniform throughout in both its chemical composition and physical state. Examples of phases include solids, liquids, gases, and even various solid phases. Now, as I mentioned in the previous slide, a phase transition refers to the process of converting one phase into another at a specific temperature and pressure. These transitions occur because the system seeks to achieve the lowest possible molar Gibbs free energy under the given conditions. The molar Gibbs free energy, often referred to as the chemical potential, plays a critical role in determining phase stability. We will explore this concept in greater detail later in this chapter. Let's look at the fundamental equation for Gibbs free energy. dG equals VdP minus SdT. This equation provides us with valuable insights into how Gibbs free energy changes under different conditions. One key takeaway here is that the first partial derivative of G with respect to T at constant pressure is negative entropy. This relationship helps us understand how Gibbs free energy behaves as temperature changes and allows us to sketch its variation for a substance across a range of temperatures. Now, let's consider two important points on this plot, Tf and Tb, which represent the freezing temperature and boiling temperature respectively. As the temperature increases, we observe phase transitions. The solid melts into a liquid, and the liquid eventually vaporizes into a gas. These phase transitions are accompanied by an increase in system randomness or entropy, reflecting the greater molecular disorder in liquids and gases compared to solids. This implies that the entropy of liquid is greater than the entropy of solid. In other words, the slope dG over dt for liquid is more negative than the slope for solid. Likewise, the slope dG over dt for gas is more negative than the slope for liquid. This observation leads us to an important conclusion, that is, the entropy of a liquid is greater than the entropy of a solid. Put simply, as the system becomes more disordered, the entropy increases. This means that in terms of the Gibbs free energy plot, the slope of dG over dt for a liquid is more negative than the slope for a solid. Similarly, the entropy of a gas being even higher than that of a liquid results in the slope of dG over dt for a gas being more negative than the slope for the liquid. This trend reflects the increasing entropy and decreasing Gibbs free energy as we move from solid to liquid to gas. Now, let's turn our attention to the region below the freezing point. In this region, we can clearly observe that the Gibbs free energy of the solid phase is lower than that of the liquid phase. This explains why a substance spontaneously freezes below its freezing point. It does so to achieve the lowest possible Gibbs free energy. Next, consider the temperature range between the freezing point and boiling point. In this range, the system naturally transitions to the liquid phase. For example, a solid will spontaneously melt into a liquid, or a gas will condense into a liquid. Again, this occurs because the liquid phase has the lowest Gibbs free energy under these conditions. Finally, at temperatures above the boiling point, the substance spontaneously vaporizes into the gas phase. This phase change also ensures that the system minimizes its Gibbs free energy, maintaining thermodynamic stability. A transition temperature is the temperature at which two phases are in equilibrium, such as freezing temperature and boiling temperature, as I mentioned earlier. A phase transition that is predicted by thermodynamics to be spontaneous might occur too slowly to be significant in practice. In other words, thermodynamically unstable phases that persist because the transition is kinetically hindered are called metastable phases. For instance, diamond is a metastable but persistent phase of carbon under normal conditions. At normal temperatures and pressures, the molar Gibbs free energy of graphite is lower than that of diamond, indicating a thermodynamic tendency for diamond to convert into graphite. However, due to the presence of a significant energy barrier in the transition pathway, the diamond phase remains stable and does not transition to the graphitic phase. Phase diagram is a graphical representation that shows the regions of pressure and temperature at which various phases of a substance are thermodynamically stable. It plots pressure on the vertical axis and temperature on the horizontal axis. In this slide, I will show you what a phase diagram generally looks like, and in the next slide, I will present 3 unique phase diagrams of 3 pure substances. Phase boundaries are the lines separating the regions of phases where two phases coexist in equilibrium. Vapor pressure is the pressure of a vapor in equilibrium with the liquid phase. As temperature increases, the vapor pressure of a substance also increases. The dependence of vapor pressure on temperature is represented by the liquid-vapor phase boundary line. Similarly, sublimation vapor pressure is the vapor pressure of the solid phase, and the dependence of sublimation vapor pressure on temperature is represented by the solid vapor phase boundary line. Boiling temperature is the temperature at which the vapor pressure of a liquid is equal to the external pressure. It is represented by TB on the phase diagram. The boiling temperature at an external pressure of 1 atm is specifically called normal boiling point, and the boiling temperature at an external pressure of 1 bar is specifically called standard boiling point. The critical point on a phase diagram is where the boundary of liquid and vapor phases become indistinguishable. The temperature and pressure at the critical point are called the critical temperature and critical pressure, and they are denoted by Tc and Pc. Supercritical fluid is a single uniform phase at and above the critical point. Supercritical fluid exhibits both gas-like diffusivity and liquid-like properties. One practical application of supercritical fluids, such as supercritical carbon dioxide, is their use as an environmentally friendly, non-toxic green solvent. For example, supercritical carbon dioxide can be used to extract caffeine from coffee and tea. After the extraction, the supercritical carbon dioxide containing the caffeine can be depressurized and separated, allowing the carbon dioxide to evaporate, leaving the caffeine behind in the container. Melting or freezing temperature of a substance is the temperature at which the liquid and solid phases coexist in equilibrium. The melting temperature at an external pressure of 1 atm is specifically called normal melting point, and the melting temperature at an external pressure of 1 bar is specifically called standard melting point. Triple point is a point where three different phases coexist. Let's examine one of the three phase diagrams. This one is for carbon dioxide. Notice the positive slope of the solid-liquid phase boundary line. This indicates a direct relationship between pressure and melting temperature. In other words, as pressure increases, the melting temperature of solid carbon dioxide also increases. Now, take a look at the triple point of carbon dioxide. It occurs at 5.11 atm and 216.8 Kelvin. What's particularly interesting about this is that the pressure at the triple point is above 1 atm. This explains why at normal atmospheric pressure, solid carbon dioxide or dry ice sublimates directly into gas phase without passing through the liquid phase. Now, let's move on to the phase diagram for water. Take a look at the solid-liquid phase boundary line. Notice how it has a steep and negative slope. This steep slope means that significant changes in the melting temperature of water require extremely high pressure. The negative slope itself is particularly important. It indicates an inverse relationship between pressure and melting temperature. In simpler terms, as pressure increases, the melting or freezing temperature of solid water decreases. This behavior is tied to the fact that matter generally compresses under pressure to reduce its volume. For water, solid ice melts into liquid water when subjected to high pressure. This occurs because liquid water occupies less volume than solid ice for the same quantity. It's a unique property of water that plays a critical role in both natural and scientific phenomena. It also implies that liquid water is denser than solid ice. Another distinctive feature of water's phase diagram is the presence of multiple solid phases known as polymorphs. Now, let's examine the phase diagram for helium-4. This diagram has several unique features worth noting. First, observe the solid and gas phase boundary lines. They never intersect. This indicates that the solid and gas phases of helium-4 are never in equilibrium under any conditions. Another remarkable feature is the presence of the liquid helium-2 phase, which exhibits zero viscosity. This phase is known as the superfluid phase. Helium-4, in fact, has two distinct liquid phases, one in the superfluid state and the other in the normal liquid state. Let's take a closer look at this video. What you see here is helium-1, the normal liquid phase of helium contained in a glass vessel with an unglazed ceramic bottom featuring ultrafine porosity. The helium-1 remains securely in the container without leaking through the ceramic base. Now, observe the behavior of helium-2, the superfluid phase of helium. Unlike helium-1, helium-2 has no viscosity. As a result, it flows effortlessly through the ultrafine pores in the ceramic bottom of the container, experiencing virtually no friction during the process. This remarkable property of superfluid helium demonstrates its unique ability to traverse extremely narrow pathways with ease. On the phase diagram, the boundary between these two liquid phases forms a distinctive lambda-shaped curve referred to as the lambda line. Helium-4 also has an isotope, helium-3, which exhibits some highly unusual behavior. Notably, the entropy of liquid helium-3 is lower than that of the solid phase. This means that the liquid phase of helium-3 is more ordered than its solid phase, a rare phenomenon. Furthermore, unlike most substances, the melting of solid helium-3 is an exothermic process, not an endothermic one. Phase stability and phase transitions of a substance are determined by its molar Gibbs free energy under specific physical conditions. This molar Gibbs free energy is referred to as the chemical potential, a term given special significance in thermodynamics. Chemical potential is symbolized by the Greek letter mu. It is important to note that matter under any given set of physical conditions naturally tends to move toward a state where its chemical potential is minimized. This principle governs the stability of phases and the direction of phase transitions in a system. Furthermore, chemical potential serves as an important measure of a substance's potential to undergo chemical or physical changes. This makes it a crucial parameter in understanding and predicting the behavior of materials under varying conditions. Let's consider an important concept related to chemical potential and equilibrium. At equilibrium, the chemical potential of a substance is uniform throughout the entire sample, regardless of how many phases are present. This uniformity is a defining characteristic of equilibrium systems. Imagine a scenario where a quantity n of a substance with a chemical potential mu1 at one location is transferred to another location where the chemical potential is mu2. The infinitesimal quantity dn represents the amount of n lost at the first location and simultaneously gained at the second location. The resulting change in Gibbs free energy, dg, due to this transfer is expressed as dg equals mu2 minus mu1 times dn. This equation highlights the relationship between the differences in chemical potential and the tendency for material to transfer between locations. Always keep in mind that the chemical potential mu is equivalent to the molar Gibbs free energy. At equilibrium, dg is equal to 0, and dn cannot be 0 after the transfer, and as a result, mu2 should be equal to mu1. Keep in mind that transition temperature T transition is the temperature at which the chemical potential of the two phases are equal. The stability of a phase depends on temperature and pressure. Let's explore how temperature affects phase stability. It is crucial to keep in mind that a substance naturally exists in the phase with the lowest chemical potential under the given conditions. The fundamental equation for Gibbs free energy is dg equals v dp minus s dt. This equation signifies that the Gibbs free energy is a function of both pressure and temperature. Building on this idea, we can derive the total differential of Gibbs free energy, which incorporates all independent variables as we discussed in Chapter 2. By comparing these two equations, we can derive that the first partial derivative of g with respect to t at constant p is simply equal to negative s. Now, dividing both sides of this relation by the number of moles n, we can express it in terms of molar quantities. That is, the first partial derivative of molar Gibbs free energy with respect to T at constant P is equal to negative molar entropy. Since molar Gibbs free energy corresponds to the chemical potential, this relation can be rewritten as rounded d mu over rounded dt at constant P is equal to negative molar entropy. Using this relationship, we can illustrate how chemical potential mu varies with temperature. On the plot, Tf and Tb represent the freezing and boiling temperatures of a substance respectively. Remember, the molar entropy of a liquid is greater than the molar entropy of a solid, and the molar entropy of a gas is greater than the molar entropy of a liquid. Similar to the Gibbs free energy versus temperature plot that we discussed earlier, the chemical potential versus temperature plot follows the same pattern. This plot illustrates that a substance spontaneously freezes below its freezing temperature because the solid phase of the substance has the lowest chemical potential. In the temperature range between the freezing temperature and boiling temperature, a solid will spontaneously melt into a liquid, or a gas will spontaneously condense into a liquid because the liquid phase in this temperature range has the lowest chemical potential. Similarly, above its boiling temperature, the substance will spontaneously vaporize into a gas because the gas phase has the lowest chemical potential. We can apply this trend to water. Below its freezing point, water spontaneously freezes into solid ice because solid ice has the lowest chemical potential. In the temperature range between the freezing point and boiling point, water spontaneously melts or condenses into liquid because liquid water has the lowest chemical potential. Above its boiling point, water spontaneously vaporizes into water vapor because gaseous water has the lowest chemical potential. In conclusion, the phase with the lowest mu at a specified T is the most stable at that temperature. Let's examine how pressure influences the melting temperature of a substance. In most cases, such as with CO2, increasing pressure prevents the formation of a less dense liquid phase. This phenomenon occurs because the melting temperature of the substance rises as pressure increases. You can verify this behavior by referring to the phase diagram of CO2, which clearly shows this trend. However, water is an exception to this general rule. Unlike CO2, liquid water is denser than solid ice. As a result, increasing pressure decreases the melting temperature of water, promoting the formation of the denser liquid phase. Previously, we learned that at temperatures below the freezing point, the chemical potential of the solid phase is the lowest, making it the most stable phase. Conversely, at temperatures between the freezing and boiling points, the liquid phase has the lowest chemical potential. Now, let us consider an important question. How are the chemical potentials of the solid and liquid phases affected by changes in pressure? Understanding this relationship will provide deeper insights into the phase stability of substances under varying conditions. As shown in the previous slide, the fundamental equation for Gibbs free energy and the total differential of Gibbs free energy are expressed as follows. By comparing these two equations, we can derive that the first partial derivative of G with respect to P at constant T is simply equal to V. Now, dividing both sides of this equation by the number of moles, N, we can express it in terms of molar quantities. That is, the first partial derivative of molar Gibbs free energy with respect to P at constant T is equal to molar volume V sub m. Since molar Gibbs free energy corresponds to the chemical potential, this relation can be rewritten as rounded d mu over rounded dp at constant T is equal to molar volume V sub m. Let's discuss how pressure influences the freezing temperature of a substance. For most substances, the freezing temperature increases with rising pressure. However, water behaves differently. Its freezing temperature decreases as pressure increases. Why does this happen? To understand, please revisit the chemical potential versus temperature plot from the previous slide. Here is the same chemical potential versus temperature plot. On this plot, below the freezing point, the chemical potential of the solid phase is lower than that of the liquid phase. Above the freezing point, the chemical potential of the liquid phase is lower than that of the solid phase. At the freezing point, the chemical potentials of the solid and liquid phases are equal. In summary, the solid phase is the most stable below the freezing point, and the liquid phase is the most stable above the freezing point. And of course, it is also the most stable below the boiling point, even if the boiling point is not shown on this plot. Now, examine this equation. This equation tells us that the change in chemical potential with respect to pressure at constant temperature is equal to the molar volume of the phase. When a substance is subjected to pressure or depressurization, the chemical potentials of both solid and liquid phases change. Since the molar volume of any substance should be positive, increasing pressure raises the chemical potential for both phases. Here's an important question. Is the degree of change in chemical potential for the solid phase the same as that for the liquid phase? For most substances, such as CO2, the molar volume of solid is less than that of liquid because solid phase is denser. This means that when pressure increases, the rise in chemical potential is greater for the liquid phase than for the solid phase. As a result, the freezing point of the substance increases. Take note that Tf prime is new freezing point of the substance after it is pressurized. Now, let's focus on the case of water, which behaves differently from most substances. Unlike substances such as carbon dioxide, the molar volume of solid ice is greater than that of liquid water. This is because liquid water is denser than its solid phase. As a result of this difference, when pressure increases, the rise in chemical potential is less for the liquid phase than for the solid phase. This behavior is the opposite of what we observed with substances like carbon dioxide, where the solid phase is denser than the liquid phase. What is the consequence of this behavior? For water, increasing pressure causes the freezing point to decrease rather than increase. This observation highlights a key principle. Whether an increase in pressure raises or lowers the freezing point depends on the relative molar volumes or densities of the solid and liquid phases of the substance. Let's examine the effect of externally applied pressure on vapor pressure. To understand the effect, we should use the relationship between chemical potential and pressure. The first partial derivative of mu with respect to P at constant T is equal to V sub m, which was derived in the previous slide. From this, we can derive the differential expression d mu equals V sub m dP. Suppose a volatile liquid partially fills a cylindrical container as shown in this illustration. In this system, we have a liquid in equilibrium with its vapor. The initial vapor pressure, denoted as P star, is the normal vapor pressure when no additional pressure is applied. Now, consider the scenario where additional pressure delta capital P is applied to the system. This increases the total pressure in the system, which affects the equilibrium conditions. At equilibrium, the chemical potentials of the gas and liquid phases must be equal. Therefore, any change in the chemical potential of the liquid d mu of liquid must match the change in the chemical potential of the gas d mu of gas. This equality allows us to relate the pressure changes in both phases. For the gas phase, d mu of gas can be expressed as V sub m of gas dP. For the liquid phase, d mu of liquid can be expressed as V sub m of liquid delta capital P. The molar volume of gas can be expressed using the perfect gas equation. So the equation should be V sub m of gas dP equals RT over P times dP. Integrating both sides from the initial pressure to the final pressure, we can obtain this equation. Since RT on the left side of the equation and V sub m of liquid on the right side are constants, they can be brought out of integral. After integration, we find that RT log P over P star equals V sub m of liquid delta capital P, which simplifies to log P over P star equals V sub m of liquid over RT times delta capital P. Exponentiating both sides yields this final expression for the vapor pressure after applying additional pressure, that is P equals P star times e to the V sub m of liquid over RT times delta capital P. This result shows that the vapor pressure increases exponentially as the applied pressure increases, as indicated by the equation. In summary, the application of additional pressure to the liquid raises the chemical potential of the liquid phase, shifting the equilibrium and increasing the vapor pressure exponentially. This phenomenon can be derived and visualized using the thermodynamic relationships outlined here. Let us begin by examining the concept of phase boundaries. A phase boundary represents the conditions under which two distinct phases are in equilibrium. These two phases are denoted here as alpha and beta. Mathematically, this equilibrium is expressed as mu alpha equals mu beta. This equation indicates that the chemical potentials of the two phases at the phase boundary are equal, meaning they are in equilibrium. Next, we turn our attention to how the slope of the phase boundary is determined. Points A and B on the phase diagram represent two adjacent states of the system that are very close to each other. The differentials dP and dt represent infinitesimal changes of pressure and temperature respectively. Since molar Gibbs free energy is the same with chemical potential, dG sub m can be written as d mu. The fundamental thermodynamic relationship governing this is the total differential of the Gibbs free energy, which is given by this. Since the chemical potentials of the two phases are equal at equilibrium, we can equate their differentials like this. We can reorganize this equation like this by factoring out dP on the left side of the equation and dt on the right side of the equation. To simplify, we denote the differences in molar volume and molar entropy between the two phases as delta V of the transition and delta S of the transition, respectively. Finally, dividing through by dt gives us the Clapeyron equation, which describes the slope of the phase boundary. This equation is crucial because it quantitatively describes how pressure and temperature are related at the phase boundary. Now, let us focus specifically on the boundary between the solid and liquid phases. For this boundary, we consider the entropy change during fusion. The thermodynamic definition of entropy is the heat observed during melting divided by temperature, which can be further expressed as delta H of fusion over T. Substituting this into the Clapeyron equation, we get this. Here, delta V of fusion represents the volumetric change during the melting process. Since the volumetric change is typically very small during melting, the slope of the solid-liquid boundary is extremely steep. This is why the pressure exerted on a substance must change significantly to produce a noticeable change in the melting point. If we rearrange this equation slightly to express the differential dP, we obtain this. In this form, we assume that both delta H of fusion and delta V of fusion remain constant. Here are several key takeaways. Number 1. The Clapeyron equation provides a mathematical framework to understand the relationship between pressure and temperature along a phase boundary. Number 2. For the solid-liquid boundary, the slope dP over dt is particularly steep because the volumetric change during melting, that is, delta V of fusion, is small. Number 3. This steep slope implies that significant pressure changes are required to influence the melting point of most substances. Understanding these relationships is essential for predicting phase transitions under varying thermodynamic conditions, which is particularly important in both natural processes and industrial applications. Integrate both sides of the equation derived in the previous slide. Since delta H of fusion and delta V of fusion are constants, they can be factored out of the integral. Here, P star and T star are the initial pressure and the initial melting temperature at the initial pressure, while P and T corresponds to the final pressure and the melting temperature at the final pressure. The integration results in this equation. This equation can be reorganized with respect to P, and we obtain this equation. P equals P star plus delta H of fusion over delta V of fusion times log T over T star. It shows how the pressure required to maintain the solid-liquid equilibrium changes with temperature. The relationship is dependent on the constants delta H fusion and delta V fusion. Now, let us examine the liquid-vapor boundary. Delta S of vaporization can be expressed as delta H of vaporization over T. Substituting this into the Clapeyron equation, we get this. The changes of entropy, enthalpy, and volume during vaporization are denoted as delta S of vaporization, delta H of vaporization, and delta V of vaporization, respectively. Since the molar volume of liquid is negligibly less than the molar volume of gas, delta V of vaporization can be replaced by the molar volume of gas, and it will lead to this, that is, dP over dt equals delta H of vaporization over Tv sub m of gas. It can be re-expressed using the perfect gas equation, so the equation should be dP over dt equals P times delta H of vaporization over RT squared. Dividing through by P, we have dP over P times 1 over dt equals delta H of vaporization over RT squared. This can be simplified to this equation, which is called the Clausius-Clapeyron equation. Be aware that the Clausius-Clapeyron equation is a specific application of the general Clapeyron equation that focuses on phase transitions involving a vapor phase. We can rearrange the equation like this. Assuming delta H of vaporization is independent of temperature, we can integrate this equation. That is, integral from P star to P dP over P equals delta H of vaporization over R times integral from T star to T dt over T squared. The left side of the equation should be log P over P star, and the right side should be negative delta H of vaporization over R times 1 over T minus 1 over T star. Exponentiating both sides of the equation gives this. This equation shows how the vapor pressure of a liquid depends exponentially on temperature. It is widely used to predict the behavior of liquids under various conditions. For the solid-vapor boundary, the analysis follows similar steps for the liquid-vapor boundary because it involves vapor phase. The only difference is the delta H. It should be delta H of sublimation, not delta H of vaporization. Keep in mind that delta H of sublimation is the sum of delta H of fusion and delta H of vaporization. Since delta H of sublimation is greater than delta H of vaporization, the curve for sublimation is steeper than the curve for vaporization. This reflects the greater energy required to transition directly from solid to vapor compared to liquid to vapor. Here are several key takeaways. Number 1. The Clausius-Clapeyron equation provides a powerful tool for understanding phase transitions, particularly in the liquid-vapor and solid-vapor boundaries. Number 2. Vapor pressure depends exponentially on temperature, as shown by the integrated form of the Clausius-Clapeyron equation. Number 3. For the solid-vapor boundary, the higher enthalpy of sublimation results in a steeper dependence of pressure on temperature compared to vaporization. There are many different types of phase transition, including the familiar examples of fusion and vaporization, and the less familiar examples of solid to solid, conducting to superconducting, and fluid to superfluid transitions. In this slide, we will discuss the Ehrenfest classification of phase transitions. This is a system used to categorize different types of phase transitions based on thermodynamic properties. The thermodynamic relation dG is central to understanding phase transitions. dG equals V dP minus S dt. By dividing both sides of this equation by the number of moles, N, we can express it in terms of molar quantities. Since molar Gibbs free energy corresponds to the chemical potential, this relation can be rewritten as d mu equals negative Sm dt plus Vm dP. Since the chemical potential mu is a function of temperature and pressure, the total differential can be written like this. By comparing the coefficients of dt and dP in these two equations, we obtain rounded d mu over rounded dt at constant P equals negative Sm, and rounded d mu over rounded dP at constant T equals Vm. In the case of a phase transition between two phases alpha and beta, we focus on the changes in thermodynamic properties. Now, focus on the first relation, rounded d mu over rounded dt at constant P equals negative Sm. For the chemical potential mu, the following holds at equilibrium. Rounded d mu over rounded dt at constant P of phase beta minus rounded d mu over rounded dt at constant P of phase alpha is equal to negative the molar entropy of phase beta minus the molar entropy of phase alpha, which is equal to negative delta S of the phase transition. This is also equal to negative delta H of the phase transition over T. Now, move on the second relation. Rounded d mu over rounded dp at constant T equals Vm. For the chemical potential mu, the following holds at equilibrium. Rounded d mu over rounded dp at constant T of phase beta minus rounded d mu over rounded dp at constant T of phase alpha is equal to the molar volume of phase beta minus the molar volume of phase alpha, which is equal to delta V during the phase transition. Keep in mind that the Ehrenfest classification is based on how the molar Gibbs free energy or chemical potential changes across a phase transition. The first order of phase transitions are characterized by discontinuities in first derivatives, such as the entropy, volume, and enthalpy during the phase transitions. The second order of phase transitions are characterized by continuities in first derivatives, whereas they involve discontinuities in second derivatives. I will cover more details in the next slide. Phase transitions are classified based on the behavior of the chemical potentials and their derivatives. This slide explains the Ehrenfest classification of phase transitions, specifically the first order and second order phase transitions. Let us explore the mathematical definitions, physical characteristics, and graphical representations of these transitions. A first order phase transition occurs when the first derivative of the chemical potential mu with respect to temperature and pressure is discontinuous at transition point. The discontinuity in the first derivatives of mu with respect to temperature and pressure is represented as this. For instance, check this mu versus T plot. The left side of the dotted line represents phase alpha, and the right side of the dotted line represents phase beta. This represents the slope of the phase alpha in the plot, and this represents the slope of the phase beta. The two slopes are different, resulting in non-zero difference. The same principle can be applied to the pressure derivative. From the previous slide, the non-zero difference between the two slopes can also be written like this. It further implies that in a first-order phase transition, quantities like delta V, delta H, and delta S at the transition are all non-zero, indicating sudden change in volume, enthalpy, and entropy at the transition point. Another unique feature of the first-order phase transition is the Cp versus T plot. The heat capacity increases infinitely at the phase transition, which makes sense because Cp is the first partial derivative of enthalpy with respect to temperature. The rounded dt is at the denominator, and since temperature remains constant, dt is 0, increasing Cp infinitely. The second-order phase transition is characterized by the continuity of the first derivatives of the chemical potential with respect to T and P, while the second derivatives are discontinuous. The continuity in the first derivatives of mu with respect to temperature and pressure is represented as this. Check the mu versus T plot for a second-order phase transition. As you can see in the plot, the slope of the curve at the phase transition is the same when approached from either side of the dotted line. Consequently, delta V, delta H, and delta S at the phase transition are all 0, indicating no changes in volume, enthalpy, and entropy at the transition point. That is, the The volumetric change at the transition is 0. The enthalpy change at the transition is 0. And the entropy change at the transition is 0. The Cp versus temperature plot for the second order phase transition shows discontinuities at the transition point. The Iran-Fast classification elegantly distinguishes between first and second order phase transitions based on the continuity of thermodynamic derivatives. First order transitions involve sudden changes in entropy, enthalpy, and volume, while second order transitions exhibit smooth changes in these properties. These characteristics provide deep insights into the physical processes driving phase changes in materials. This slide provides an example of a second-order phase transition characterized by a symmetry change, specifically from a tetragonal structure to a cubic structure as the temperature increases. Let's break this process down in detail. At lower temperatures, the material exists in a tetragonal phase, where the physical properties such as expansion or deformation differ along different axes. As the temperature increases, the material transitions into a cubic phase, which is more symmetric. In the cubic structure, the properties along all directions become equivalent. This process involves gradual adjustments in atomic or molecular positions as symmetry increases. Fast changes occur along some directions, represented by the long red arrows. Slow changes occur along others, represented by the short red arrows, indicating anisotropic behavior during the transition. At the cubic phase, the changes in properties along all directions become equal, as shown by the uniform red arrows. Lambda transition is a key feature of second-order phase transitions. Unlike first-order transitions, the heat capacity Cp diverges to infinity at the transition temperature. This is shown in the plot where Cp peaks sharply at the dotted line, representing the transition point. Such divergence arises from the critical fluctuations in the system as it reorganizes itself during the symmetry change. Some notable examples of second-order transitions include order-disorder transitions and fluid-superfluid transitions.